First, let me introduce a little bit of myself. I'm original from Japan. I moved to the US a couple years ago. And I was working for a second-hand marketplace app called Mercari. And just a week ago, I left the company and joined this new company called Chanoma. And this company actually creates a service called the Chomp. And it's a camera app for sharing food, photos, and with your friend or family with using the app. And unfortunately, the service doesn't have the Android app because I'm the first Android engineer to join the company, and I'm still working on this. So stay tuned. And today, this presentation starts from the story about the intern I mentored. This intern was just graduated from college, and he has a little bit of experience of coding. But he's very new to Android. And he came to me one day and said to me, hey, I want to build a camera app. It's like a Snapchat. And okay, that sounds good. Tell me a little bit about it. And then he told me, well, it has the camera, and you can just take a photo very quickly. And maybe it will have some kind of filter. And then so you can play around with it. So I felt like this is really Snapchat. But anyway, and then he asked me, I saw that Camera1 API is deprecated a couple of years ago. So I want to learn about the Camera2 API on Android to implement this. And how can I start? I gave him a book to read on Android and looked at the book, but it didn't have the description about camera. So we went to our source of truth, Android dev document, and found out that Camera API document hasn't been updated for a while for Camera2 API. And also, we look at this list of the classes that Camera2 API has, and the intern actually got really overwhelmed by how many classes that he needs to look into just to take a photo. Yes, Camera2 API gives her great access to lower layer level things, but in fact, that makes really hard to control by yourself. And then I recall there's a sample app that Google created, and then we looked into that and found out there was a Kotlin code which had 800 lines of code. And so finally, this intern decided to stick with Camera API 1 for now because the Camera2 API was a little bit hard for him. And that experience was actually started for me because he was willing to learn Camera2 API. But in fact, I couldn't give him a good source to learn Camera2 API. So in this presentation, my motivation is to help developers learn and how to use this API from the ground without using library. In Japanese martial arts, there's a step to master things. I want to follow that step to master Camera2 API in this presentation. First, shoot. Shoot means to keep and understand the basic. Here, I want to talk about how each classes and callbacks work and how to calculate preview sizes, which is really a pitfall for learning Camera2 API. And second, ha, it means to break the basic. I will talk about how to customize settings, such as adjusting preview sizes or controlling auto exposure to build your own camera app. And third, it means beyond the basic. I want to dive into more advanced topic using OpenGL. Okay. So for the reference, I have created a sample code, which I forked from Camera2 basic sample from Google. But I made it a little slightly better. I made camera class independent, and callbacks are slightly organized so that it's easier to follow. And I made it some features like manual focus, white balance adjust, and also I added some Kotlin extensions so that it will simplify the code base. So now let's get into the first step, understanding the basic. Here, I will explain two things, as I mentioned. The first is about callbacks that Camera2 API has. The second is how to calculate the preview size. Let me quickly go through Camera2 API architecture first. There's a lot of things underneath this. The bottom layer, the purple one, these are the actual device that Camera has. Since Android has many devices all over the world, and there's many image sensors, so it's very good idea to have this kind of abstraction layer on it. And there's also the on top of that, there is a camera service class which is written in C++. We won't usually touch this hardware layer or C++ layer unless you're like device manufacturer to actually change these settings. So I won't go through this part. Then there's a wrapper layer, which is written in Java, and this part is what we call Camera2 API. So as you can see, one of the reasons Camera2 API was introduced is to give developers access and control lower layer from Android framework. Well, side effect is though, there is so many callbacks, and there's so many API access. This is really hard to organize. For example, before you're starting the camera device, you need to check camera device state callback. And when you take the preview of the picture, you need to look into the camera session capture callback. Or let's say you want to take the high-speed camera, then you have to look into camera constraint high-speed callback. Okay, so that was pretty long, but so in fact, knowing how each callbacks interact with Camera2 is quite important to understand the Camera2 works. So first, I'm looking into how to launch the camera. And you'll see the multiple callbacks even in this process. First, we need to prepare two things at the view creation. First one is a texture view, which is the view that camera image get rendered. And another one is a camera manager, which access to the camera service. And we can create this from system service. And the first callback we will see is a surface texture listener. This listener returns on surface texture available when texture view surface is ready. Let's look at what we're doing at this open camera method inside. Here we're doing multiple things, so I'm going to look into it one by one. The first one is set up camera output, which means we calculate the output of the preview size based on the size of texture. So that's why we are giving a width and height as a parameter. And then the next one is configure transform. This is the way we transform texture matrix based on the display's rotation. I'm going to explain about this too later, so let me keep going for now. Once the preview size is ready, we're going to open the camera. Let's look into this method now. First, we're going to acquire a semaphore lock so that other process will not access the camera device while we're trying to open the camera. And then we start the background thread handler. Because all the camera API requests happens on the one thread, we need to create a background thread to actually manage the asynchronous process. And then once the background thread is ready, we call the open camera from the camera manager, and which returns the camera device as a result. So here you can see the camera device is coming back from this camera state callback. And once camera device is ready, then we can unlock the semaphore. And then, now we go back to the open camera part. Then the next step is to start camera preview using the camera device. For preparation, we set default buffer size on surface texture from the previous size that we just calculated. And then we go to the start, the camera part. Here, before we start the preview, we instantiate the image reader, which is a class to get an image result from camera device. And we call this here because we want to build, we want to bind this to create capture session, because after a while, we want to take a picture of it. And then the callback comes back again, which is a capture session state callback. And finally, we're ready to preview capture session. Here we can see there is a 4-state callback that we have to listen to. And that's pretty big, but we're still at the stage where we just take the preview. Now the next step is taking photo. So taking photo is slightly simpler than the previous step because there's only one session and one callback. Let's look at the code. First, we create a capture request from camera device. And then we bind surface that we want to get the result from and the request parameters. In this example, I want to get an auto exposure. So I'm adding this control A pre-capture trigger start as a parameter. And then we call capture session capture to trigger the request. And then the callback, which is a camera capture session capture callback. And this is actually the returns the result of the capture session. And every time you request the focus or the auto exposure or taking a still picture, you will run this same process, which is capture and then the callback. And however, this makes really screwed up when you try to actually implement. Let me show you in an example. First, check autofocus. We can check the autofocus using this top capture result, and then we get the result from capture result.control AF state. And then once focus is locked, then we look for auto exposure, and we also can get the result from control AE state. And then once auto exposure is ready, we can capture still picture. If auto exposure state is inactive, then we have to ask for the camera to actually request the exposure. But one problem we have is autofocus is sometimes no at the first place. So in that case, we need to keep requesting the auto exposure until the autofocus returns something. And then there's a pattern we should not forget, because sometimes some devices does not support auto exposures. So we do need to handle that case as well. And also, the auto exposure might request flash, and we need to handle that case to actually request for the flash or just keep going and take a still picture. And you know what, this doesn't work really. It can easily create a spaghetti code, and you can never add new features. So what we have to do here is to add a state for the camera to request, to simplify the request. We define state enum by ourselves, which is first one is like preview, and the next one is waiting lock. Third one is waiting pre-capture, and then the fourth is non-pre-capture, which is one step before the picture is taken, and then the last one is picture taken. And every time we make a request, we check which state we are at, and then check what we need to check. This will simplify the code. So let me look into each process. First, we lock our focus of our camera. And then here, we actually change the state to waiting lock. And here, again, we capture, and then the callbacks returned. And here, we also set so the recent devices usually support auto exposure. So in that case, we can just add control F mode auto as a parameter so that we can actually request the autofocus mode. And then we go to the waiting lock state, and then we check the multiple states. Because autofocus sometimes does not work, maybe the screen is too dark and it's not inactive, you cannot get unlocked. You need to handle that case, but here in this example, I just keep going because we don't want to block users taking a photo. So we go to the next step, run pre-capture. Now, pre-capture is a stage where we request auto exposure. Just like we did at the forecast logs, we add control AE pre-capture trigger for the auto exposure. And then at the state of waiting pre-capture, we also check the state. As I mentioned, sometimes the device doesn't have the auto exposure feature, and then in that case, this state will return null. We check the null status. And then there's also other cases that the auto exposure requires flash, or even the process might take longer than usual. In that case, we just skip to the stage waiting non-pre-capture. So this state is actually waiting for the auto exposure to actually finish, which is converge state. And then once that's ready, we take the capture still picture finally. And here we do we add the capture request as a template still capture. And then we take a photo. And we usually have this, there's an image reader that I mentioned. This returns the callback called onImage available listener. And then here we can pass this result, the image result, to handle image, and you can save the image whatever you want. Oh, that was pretty long and pretty big chunk of code, so I won't have that much of code from now on. But next, I'm going to talk about the preview of how to calculate preview size. Because there are thousands of Android devices in the world, you can easily get screwed up with this sizing issue. Like when I'm building my camera app, I always have the issue with aspect ratio is not correct, or the width is not adjusted as screen size. This kind of issue happens a lot. So I want to share the logic behind calculating a correct preview sizing. Step to adjust preview size, there's 3 steps that you have to follow. First one is to calculate view rotation, because the image sensor sometimes has a different rotation degree compared to display size. The second one is pick up the supported preview size from camera, because the camera usually supports multiple preview size, and we need to pick up the good one from here. And then finally, we adjust the texture view to fit the preview size. First one is calculate view rotation. So there's a sensor rotation that we need to think of. Sensor rotation is an angle that needs to be rotated to get the upright image. So in this example, actually when you take the camera, camera sensor capture is horizontal of the image. But if you want to get the correct image output, you need to make a rotation. And this sensor orientation will tell you that. And also there's a display orientation, which you can get from Window Manager. And this is pretty straightforward because it's the actual view rotation. So when it's portrait mode, it's 0. So when we compare this camera device world and display world, the camera device world is a camera sensor world. Sometimes it's not in the same shape. Let's say in the Pixel 3, sensor orientation is 90 degrees. So when you actually want to check the optimal size, you need to swap the width and height. So that's what we're doing here. We are passing texture view width as a texture height and texture view height as texture width. And for the same one for the display size as well. So that's the first thing you need to care about. Now let's go to the fetching supported sizes. Here, you can fetch the data from using a camera characteristics class. And then you will have the key called scalar stream configuration map. And this will return the supported preview sizes. I got this from Pixel 3. Now, you have to choose the right preview size from here. The first step you can do is actually define the max size because some devices actually do not support the large screen because it doesn't have much memory. So best scenario is to have the probably the 1920 by 1080 size of the maximum so that we can kind of get rid of the issue with memory issue of the memory. And we filter out the R too large. And the next step is to pick the one the aspect ratio actually matches. And how to decide the aspect ratio of preview is there's a way to do it. The easiest way is to choose the largest one that the actual device supports because this list of device is actually the size of the sensor, image sensor. So image, we want to have the ratio of image sensor. So in this case, 4032 by 3024 is the largest one, and we choose the aspect ratio, and it's 1.33. Now, with this condition, we can reduce the supported preview size down to 5. Now, we go to the, we then choose the closest one from here. And the one closest here is the, it really depends on like how much size that this list supports. But if candidates are larger than the texture size, you pick the smallest. But if the candidates are smaller than the texture size, you pick the largest. In this case, 1280 by 960 is the closest one we can get. So this is actually the supported preview size that we have. Now, based on this preview size, we can now adjust the text view size. 1.33, and then we get the 1436. That's the actual texture view size based on the aspect ratio. So this is how to calculate the preview height. Now the basic is over. You understand how to use the callbacks and how to use the preview calculation. Now we break what we have just learned. I'm going to break from the 3-part. First, implementing full screen preview. So we are not going to use the we're not going to adjust the text view size. And the second one is controlling exposure mode, and the third one is a manual focus. First one, in the Google Samples app, camera preview is always adjusted with width. However, having a full screen preview is better for the user experience because it can capture a lot of things in the site. Let's try to change this. First, for the requirement, we want to change the theme that we use to window transparent status. This will change the actual window size. It will not overlap the navigation bar, but it will overlap the status bar. And this helps us to calculate display size correctly. Now, the full screen preview, we can now calculate the preview size using a window size. For the example of Pixel 3, window size is 1080 as a width, and 2160 is a height. And so that we know the aspect ratio of this screen is 2.0. And the 2.0 and the closest aspect ratio here is 4000 to 1000. Now, using this aspect ratio, and also we set the maximum height and width, we can calculate for this. And we actually choose the, oops, I think I skipped the part. Oh, no, I'm good. Okay. So the next one I'm going to tell up is to change the camera control mode. So in this example, I'm changing the white balance to light mode, sunny mode, and cloud mode. So how to change the camera mode is first, you need to know what kind of mode is supported on your device. And the second one is to add parameters against request builder and then use the set repeating request, just like we did in the preview. So to know what kind of mode is supported, we can use camera characteristic.get method. And this returns, based on the key you input, I can return camera metadata, it can return range, region, integer, whatever. So if you want to look for the auto exposure mode, we will input the key of modes. Here in this example, we put the camera characteristics control AE available modes. And the result we get is 0, 1, 2, 3, 4. It's a number. And we don't know what this is. So we look at the Android document. Now it says, in the document, it says any value listed in Android.control AE mode. So I just click this one. And then it takes me to capture requests document for somehow. And then there's a list of that's been supported. But still, I don't know what the number means. So I clicked one of them. Now I get the result that control AE mode on is actually constant value 1. So I know that each number represents off, on, auto flash, always flash, or auto flash red eye. So it's kind of, it's a bit of tedious to figure out what is returning. I was looking for the response of camera characteristics, but then I had to look into camera request and camera data. So it's really kind of confusing part. But anyways, I'll just mention, camera request is a subclass of camera data. That's why we have to look into both documents. So to get a mode, we need to request the get modes from the camera characteristics, and it returns the camera metadata, and then we can request that value to actually request the camera. So as I mentioned, that the camera capture request is a subclass of camera metadata. So you can basically call camera metadata dot control F trigger start, but it kind of makes you confusing. So I think I would suggest using a capture request dot control F trigger start for here. So let me just quickly add white balance sunny mode to camera. At the on click, I change the white balance mode to sunny. And then I open camera because we want to re-request the capture session. And then inside the camera, we add this control AWE mode to control AWE mode daylight. And then we start the requesting again. Now, as you can see, when I'm making a tap, and the focus and exposure actually changes to, and I cup the glass and it changes again. So this is what I want to do. Before we go to the manual focusing, we need to understand how the camera metering works. So the camera metering is a process of determining aperture and shutter speed, depending on the light that goes on the camera sensor. So on Android, we can set up the code, this area focus, using control AF regions. And here, we look at the metering rectangle. A metering rectangle can set a weight value. like we do it here. I put the 500 here. It's a 0 to 1,000 range, and you can place it as much as you want, as long as it won't go to the maximum of the range that the camera device actually supports. And this weight is relative. So in this example, I put 2 measuring region, which means it will that the device will look into the focus of this A and B part, because the other part has a rate of 0. So this is how the focusing and exposure works. And also you need to know that the world of image sensor and screen is slightly different, because when you tap the screen like 500, 1,000 part, in the sensor, it's not that, it's actually different. So you need to actually adjust the size. And so you need, to get the actual place in the image sensor, you can use the sensor info active array size. Using this, you know that which part of the sensor you're touching as a screen, and then you can make an adjustment for it. Okay, now this is the last topic, Li. Li is a beyond basic, using filters with OpenGL. So let me explain what will be added to render OpenGL screen. So this is the actual regular camera stream. This is actually there's a texture view and there's a surface texture on top of it, and camera device will serve the camera strip on this surface texture. But when we want to run the OpenGL, we need to add extra layer called window surface, which is layer that actually handles OpenGL. This layer actually has a multiple texture on it, and we use one of those textures to actually render the camera using the camera device stream. For the window surface, I will not explain, but if you're interested, there's a good example on the Google sample app. It's called Graphica, and you can look into the source code. And here's a diagram that shows the flow of camera launch. Usually, when the surface texture is ready, we open the camera, we start background thread, and then we do all the preview calculation and whatnot. But when we want to use the OpenGL layer, we need to intercept that process. First, what we have to do is set up the EGL and the window surface. EGL is an interface between the OpenGL and native Windows system. It's providing a mechanism to actually creating a render surface. This is why we need to pass a surface texture to render the OpenGL part. And then on the window surface, there's a multiple texture you can set. And then we need to instantiate that texture layer to use it. And then the next step we will do is set up the surface texture. As I explained, we need to use the surface texture to render it, but the OpenGL has a texture, so we need to actually wrap the render and then pass it to the camera. And the third step is loading shader. Because the OpenGL actually requires the way to show the image with the aspect of OpenGL world, and then we need to actually calculate the color to see it on the screen. So there's a two-step of shaders that we need to introduce. First one is a vertex shader. It's a render graphics with a given texture coordinate to transform the matrix. And the second one is a fragment shader. This actually renders colors. Let's say there's a two object, and then it overlaps it. This fragment shader will dictate how to actually change the color for each pixels. Now, once those shaders and all the OpenGLs are ready, we go to the regular process that we do for the previewing the camera. Now I'm going to show the demo. Yeah, I have this real-time demo that I want to show. Is the actual adding a filter and then showing the, let me see if I can do it. So this is a camera I have right now. And then I added the filter. I added the button here. So this is using the OpenGL filter to actually change the filter of it. And I take the photo like this. Yeah, of course you can do the recording, and that will be the much better cool experience. Anyway, so that's a demo. And let me go back to the. Okay, so the wrap up for this presentation. Learning callback is the closest way to understand the Camera2 APIs. I think you have seen like 7 callbacks in this presentation. But understanding how it works, it helps you to learn like how the flow works. Second is to understand the camera sensor is really different from the display screen. So you need to understand the difference between it, and sometimes you have to consider the calculation to adjust the size and whatnot. And the third is to write sample app by yourself from the ground. That will help you actually understand how it works. I had to use the mic, so there was 3 things I talked about for the wrap-up. But for the reference, I have a couple of references that is a good source to learn. First one is to actually to use the Camera2 API, you need to learn about the camera. Like you need to learn what is auto exposure is, what is metering is, and there's a good link that you can find to learn about this. That's the first one. And once you learn kind of how to work with it, I don't think the Google document is really good for beginners, but once you know how to use it, you go back there and you know like what's like how they're trying to implement the camera. So it's a good reading. And for the OpenGL, of course you need to look into the OpenGL for the document, other the shaders, and also there's a good sample app from Google Creative Lab. I'm very I referred a lot from this sample, but there's a shader cam which you can use. So this is end of my talk. If you have any question, please, I'm welcome to answer. But thank you for coming and enjoy the rest of your conference. Thank you. So the question was, when I use the OpenGL filter and then take the picture, does it keep the filter? The answer is yes. So as I mentioned, so the image, when you save the image, we use the image reader, and we add that image reader against the camera capture method. So we bind it. So what image reader get is the image, the same image as the what camera is showing up. So does that answer your question? Yeah. So it's basically yes. Is the answer. Yes, you can use OpenGL. You mean, so the question was, can you add object on the camera using OpenGL? And the answer is yes. So as I mentioned, there's multiple textures that you can use on OpenGL. And you can use one of the textures of that to actually render like frames or icons. And you can use that as well for that use case, yes. Actually, I only used 2 devices, which is Pixel 2 and Pixel 3, which I had as an actual device. No Samsung, yes. But yeah, yes, there's a lot of hard things about many devices. Yes, I have the code that has like if Samsung and else, yeah. Yes, well, there's a very good library such as Apparat. I think that it's called Apparat. There's a Photorat. And there's a couple libraries that you can use, and it has a simple interface. It wraps all the things, the complicated things here. Yes, it is compatible to one. Because the Camera2 API supports from the API 21, so which is Android 5.0. So it's basically backward compatible, but I would suggest upgrade your app to above 5.0 because we don't want to support 4.x anymore, right? It's 2080, so. Okay, so the question was, Camera2 API is really hard. What the developer can do to actually use the Camera2 API? Is that the question? Yes. I don't think there's a good way to use Camera2 API, but there's a good information. I went to Android Dev Summit 3 weeks ago, and I asked the Android Dev team if there's any plan to include the Camera2 API into Jetpack. And they said, yes, they're planning to do that, but it's still on its way, and it might take like a year to actually include it as a part of Jetpack. So once that's been out, then it might be much easier for us to use it on ourselves.